Hello students, um, welcome again. I am Ravi Ranjan Kumar and I will be continuing with last session of work power energy, and that will be concluding as well. Okay, so without losing any further time, let's start our discussion. In today's lecture, we will try to cover vertical circular motion or circular motion in vertical plane, and then we will talk about the relationship between a conservative force and the potential energy. Okay, so let's now discuss. So let me share my screen with you people. So let's start the discussion of circular motion in vertical plane. We will start with the most simple case over here. Say we have a simple pendulum. Okay, so that is a bob of, let's say, mass m is suspended with a string of length L, and this string is attached to a fixed point, say O. So if we impart some velocity to this bob over here, okay, it is constrained to move in a circle of radius L. As long as there is any tension in the string, okay, this bob will move on a circular path. If this string somehow slackens, it loosens up, okay, then it will move inside this circle over here. This circle has O as center and L as radius. Okay, so here, in order to study this problem over here, okay, let's say like this particle, this bob over here is projected with some initial velocity u. Okay, so at any instant, let's say it continues with circular motion, and at any instant the string is like this over here and this bob is here, and let's say this is making an angle theta with the vertical. Okay, so at this instant when the particle is over here, we are interested in that what would be the velocity over here of this particle, and what will be the tension in this string. This is two major things we are looking to find out. So how are we going to find out these two quantities? In order to do this, we need to understand the dynamics of motion as well as energetics of motion. So let's first try to look into the dynamics of this motion over here. Let me choose some other color pen over here. So this particle, this is the particle of mass m. So obviously it will be having some weight over here. Let's say mg you say, and the tension will be acting in this direction, and obviously since this is moving along a circular path, it will be experiencing a centrifugal force, and since the velocity, the tangential velocity at this point is v, so this would be equal to mv square by L. Okay, so this angle here would be theta as well. So when we will consider the force balance of this particle along the radial direction, it will give us T will be equal to mv square by L plus mg cos theta. So that would be the equation of force. That is what we have derived from studying the dynamics of this particle. So this is the tension in the string when the string is making an angle theta with the vertical. And the another equation we will be looking for, since we have two unknowns, two equations we require. So another equation we will find out using the energetics of this situation. So here, okay, the initial position of this particle is here. Let me use again another color pen. Okay, so initial position of the particle is here and the final position is here. So it has moved from this level to this level. So the height it has ascended. So that simply we can write it as h will be equal to L into 1 minus cos theta. This is the height ascended by this particle. So obviously here we can see that as the particle moves from this initial position to this final position over here, its potential energy is going to increase, and using principle of conservation of energy, you can say kinetic energy will be decreasing. That means the speed will be decreasing as well. So using conservation of energy over here, which says delta U plus delta K is equal to 0. So a decrease in kinetic energy, we can say that is half m uh, u square minus v square, that would be decrease in kinetic energy, and that will be equal to increase in potential energy, that would be mgh, or you can say mgl into 1 minus cos theta over here. So that will simply give us like v square will be equal to u square minus 2gl into 1 minus cos theta, this relationship. So this is equation number 2. So whenever we are required to find out the tension and velocity at any point, we are required to use these two relationships. Let's take one more situation here. The particle I have taken is in the lower quadrant. Before moving to the next situation, let's try to analyze this relationship over here a little bit. So looking at this equation of tension over here, what we can say, like in the lower quadrant, as long as this equation is valid, okay, this quantity is definitely going to be positive. In the lower quadrant, this quantity is definitely going to be positive. In extreme situation at theta is equal to 90 degree, it is going to be 0, but for theta less than 90 degree, it is going to be positive. And this quantity, since we have a v square term, so this quantity will also be going to also be greater than equal to 0 over here. So this quantity is greater than equal to 0 and this quantity is greater than equal to 0. So as long as if theta is less than 0 over here, in this situation, what we can say, the tension cannot be 0 over here. Tension anyway is going to be positive always. So the conclusion is the string will not slacken, never slacken, as long as this particle is in the lower quadrant. Okay, tension will never be 0 as long as this particle is moving in the lower quadrant. Okay, like the V can turn out to be 0, but the tension in the lower quadrant cannot be equal to 0. And now let me take one another situation when the particle will be in the upper quadrant. Let me draw that diagram again. Okay. So initially the particle is here, mass is m, and it is projected with velocity u, and this is say center. And finally say it comes over here, and let's assume this angle as theta. So when the particle is here, okay, let's try to write the dynamics and energetics as well. Okay, so here the force acting would be nothing but mg over here, and let's say velocity over here is v. So centrifugal force would be acting in this direction, that would be mv square by L, and the tension would be in this direction. So this is the tension. So here the equations, this angle is theta. So here the equation of force would be T plus mg cos theta is equal to mv square by L. Okay. So here Here what we can conclude first of all, that since in the lower quadrant we already said that the tension cannot be zero, and looking at this equation over here in this situation, like mg cos theta would be greater than zero as long as theta is greater than zero, means it is in upper quadrant, and tension can never be negative, so it is also greater than equal to zero. Okay, so here we can conclude that this v term, the speed of the particle, can never be zero. V cannot be zero. The speed cannot be zero in the upper quadrant. Like, we are going to use these two information, like tension cannot be zero in the lower quadrants, and V cannot be zero in the upper quadrants. That is going to be very, very useful for our discussion and vertical motion and circular plane. So, and another equation, obviously the equation of energetics. So this is the level, initial level, and this is the final level, and this time h is gonna be equal to, that would be this time L into 1 plus cos theta over here. So using work energy theorem or conservation of energy, finally we can conclude that V square is equal to U square minus 2gl, and this time we will be having 1 plus cos theta. So these two equations will enable us to find out for tension as well as the speed at some position over there if the particle is projected with some velocity u, tangential velocity, at lowermost point. So let's have some results over here for different value of let's say one situation let's take. So this is the situation I am taking. Let's say I will be taking this as theta over here. So we need to find out the value of u. Let's say the question is, with what initial velocity from the lowermost point it must be projected tangentially so that it covers theta angle. Okay, and I'm going to summarize the result as I have already written the equations over here. So I'm going to summarize this result in a table. Okay, so for example, here I am taking theta, and here I will take, let's say, uh, at this point our speed is v, and at this point our tension in this string is t, and let's say we are required to find out the initial velocity. So if we want that this particle moves still here, like it covers this quadrant, okay, of theta is 90 degree over here. So at theta 90 degree here, looking at this expression, the first expression which we wrote over here, in this case, the equation of tension over here, this suggests that um, t here will be equal to 0 and v here will be equal to 0 as well. Let me write it over here. T would be 0, v would be 0, and that would be giving us, after solving all the equation, it would give us, that would be root 2gl. Okay, and if we want to project it such that it finally reaches this point, means like theta is equal to 180 degree we want to take. Okay, so in the upper quadrant the velocity cannot be zero over here. The velocity cannot be zero over here, only the tension could be zero. At this point the velocity cannot be zero, tension would be zero. So using the equation, the dynamics equation in the upper quadrant, we can very well find out the value of v over here, and that will come out to be root gl, and u will come out to be root 5gl. And these are very standard results, and all of you at least must remember this result over here. The meaning is like uh, again looking at the same situation over here. So if this is a vertical plane, and if we have projected a particle with velocity u. Okay, and the first situation I will say that if u is less than root 2gl, if u we have just learned that if u is equal to root 2gl, let's write the equality also. So for u is equal to root 2gl, the particle will reach over here. At this point, the velocity as well as tension will become zero. But if u is less than root 2gl, the particle will reach somewhere over here, and at this point the tension here will not be equal to zero, definitely, because in lower quadrant tension cannot be zero, but v finally will become zero. So by reaching over here, it will again turn back, and it will come back here, and it will move in this direction, it will move in this direction, and now here at this position it will have speed u in backward direction, and it will move in another direction also. So the motion here we are looking for, motion will be oscillatory, the motion of a pendulum. Okay, so this is the first situation. And the second situation, if u is greater than root 2gl and less than, let's say, root 5gl, so it will reach somewhere over here. Let me use some other color pen. So it will reach somewhere over here. It will move in the upper quadrant over here. It will move in the upper quadrant. And at this final position, what we will be having, like let's say this is v and this is t. So we have learned the circular motion will cease to happen when tension will become zero. So at this point, tension is going to be zero over here, and at this point tension will be zero, but velocity or speed will not be zero over here as well. So here, although the string will become slackened, but there would be some initial velocity, some velocity over here. So due to this velocity, but afterwards it will be moving under the influence of gravity only. So when a particle is projected with some velocity v and at some angle, okay, so its motion can be described as projectile motion. So the motion beyond this point is going to be projectile motion over here. Okay, so we will take one case. Like this seems to be very interesting situation. So we will be definitely taking a problem on this. So a little bit later. So before that, let's complete the different case scenarios. So here, if u is less than root 5gl and greater than root 2gl, motion will be circular till this point, and later it will be projectile, we can say. Okay, and it will continue to move along the parabolic path until this trajectory tries to cross this circle. So once this tries to cross this circle, the tension, there will immediately come an impulsive tension over here, and then it will continue to move on circular path and so on. So this is the second case scenario. Now let's look at one more case scenario. The third scenario is if u is greater than equal to root 5gl. So in this situation, we have seen that if u is equal to root 5gl, it will reach the topmost point. And at the topmost point, although there would be some velocity left, there would be definitely some velocity left, so v is not equal to zero. So when it will move beyond this point with that velocity, tension will immediately come and it will complete the circle. So root 5gl is the velocity with which it should be projected to complete the circle over here. So the particle will complete the circle. Okay, so this is the situation. And now let's discuss one problem, one simple problem over here. That is very simple. And the situation is this question. Sorry. This question is a pendulum. String length is L. Bob of pendulum is given a speed u is equal to root 4gl, and it is at its lowest point. Let me describe this question figuratively. Okay, what it says. So it says simply, let's say we have a circle in vertical plane, and here it has been projected with a u is equal to root 4gl. Okay, now it's asked us like whether it will complete the circular motion. So the answer is definitely a no, because as we have seen, like if the velocity lies between root 2gl and root 5gl, okay, it will move to the upper quadrant, but somewhere it will, the tension will become zero. We have studied that over here. So since u is equal to root 4gl is definitely less than root 5gl, so at some point over here tension is going to be zero. Okay, and we just need to find out the corresponding value of theta over here. Okay, and the so that is what the second part of the question is asking. Find the uh, uh, if no, where will it leave the circle? So it will leave the circle somewhere over here when tension becomes zero, but velocity will remain something like there would be v, like which we need to find out over here. Okay, so here when we can write the equation of dynamics as well as as well as energetics over here. So first of all, let's try to find out the value of v. So value of v, how can we find out? Using a simple principle of conservation of energy. So v square we can write simply as u square minus 2gl into 1 plus cos theta. We can write L is the radius of this circle that we have learned already. Okay, and so this will give v, because u we know in terms of theta. Okay, and the another equation, the equation of force, we can write over here. So here the equation of force would be simply mg cos theta would be nothing but mv square by L. Okay, so using this equation number 1 and equation number 2, we would be getting cos theta as cos theta as 2 by 3. So basically theta, we can say that would be cos inverse 2 by 3. We have got this relationship by solving these equation number 1 and equation number 2. So now it has been asked to us, and also we here we can find out when we will be substituting the value of theta in this equation, the value of v we can find out, or value of v here would be nothing but u square, which is nothing but 4gl minus 2gl into 1 plus, and cos theta is 2 by 3. So this will give us that is 4gl, and that would be 5 by 3, so 10gl by 3. So that would be 2gl by 3. That would be v square. So obviously v will be equal to 2gl by 3 root under over here. So now the later part asks us like what would be the maximum height of the particle from the lowermost point over here. So in this circle, let's draw a larger circle this time. So we have already seen that it has lost tension over here. Tension has become zero over here at theta is equal to cos inverse 2 by 3, and v is equal to root under 2gl by 3 over here. Okay, so here so now afterward this motion would be projectile. This motion would be projectile over here, and we, this is the topmost point. So first of all, the point of projection of the projectile, this point is going to be that we have already understood that this is going to be L into 1 plus cos theta. We are required to find out this additional height, which is the maximum height of the projectile in this case over here. So for the maximum height, we use the formula u square sine square theta by or here we must write v, because at this point we have written velocity as v divided by 2g, and the value of v we know, and the value of theta we know, and everything else we know. So h, after calculation, it will give us 5l by 27, and the maximum height that we are looking for now is nothing but this l into 1 plus cos theta, and both this quantity like l into 1 plus cos theta plus this 5l by 27, and this calculation will give us 50l by 27 over here. So that's very easy for us to solve now. So this is the case we have taken. Okay, so this is motion in vertical plane here. So now let's say, like, can we extend this concept to some motion of the simple pendulum in some inclined plane? And another question which I have selected for the discussion is this one over here. So see, in vertical plane, we knew how to write the equation, and this is a question of the inclined plane. Let's look at the question first. So here what we are having, two particles of same mass. So we are having two particles of same mass, let's say m, connected by means of light thread of length L. So this is length L, and is kept on an inclined plane of inclination 37 degrees. So this theta is given to us as 37 degree, and the coefficient of friction between A, this is A, so there is some friction between A and inclined plane, but there is no friction between this B and the inclined plane. Okay, so uh, this is A over here, which might be fixed due to friction over here. And what we are to find out is find the minimum value of mu for completing the circle by B around A. So like what we are going to do in this question over here, although this motion is not in a vertical plane, but it is on the inclined plane, but using one small modification, we can use the above equation that we have learned in this situation as well. Okay, the thing is, for example, if this is inclined plane over here, okay, and this theta is given to us, so basically g, the gravitational acceleration act in this direction, so we can basically resolve this g into two components. Okay, and this angle would be theta as well. So this component, basically we will be able to write g sine theta, the component of g along the incline, and this component is definitely going to be g cos theta. So when we were looking at the circular motion in vertical plane, there were a lot of expression in which there was g was present. So in this case, we will be simply using g effective, that would be down the incline. Okay, and everywhere wherever we had g, we will be replacing it with g effective, and its value would be g sine theta. In this case, it would be sine 37 is 3 by 5, so that is going to be 3g by 5, and this quantity is going to be 4g by 5. Now say um, we want to find out the minimum value of mu for that, for completing the circle. So now let's take this situation. So let's say this circle we have drawn on the inclined plane, and this is g effective, that is 3g by 5, and so say, let's say particle is over here. Okay, so what we can say, that at this point over here, what should be the tension would be maximum at the lowermost point, and whenever the tension is maximum, okay, the another particle will experience the greatest pull, so the chances of slipping on the surface would be maximum at this orientation only. So we need to first of all find out this t over here. Okay, and then we can draw the free body diagram of this particle as well, and then we can find out the minimum value of mu. So how are we going to find out this t? So we have to find out like what should be the value of u over here such that it completes the circle. So previously we knew that this u could be like root under 5gl, that is the minimum value of u to complete the circle. But in this case scenario, since this is the motion on the inclined plane, we must replace this g with g effective. So that will give us what we can say 5 into 3g by 5 into L. Okay, so that would be simply root 3gl, we can say. So this will be the minimum velocity that must be projected to complete the circle. In that case, the tension, so see at this position the weight is going to be a weight down the incline, we must say. So that would be mg effective, and that would be nothing but 3 mg by 5. So in that case the tension we could write would be nothing but g effective, that is 3 by 5 mg plus uh, mv square by L. So m by L into 3gl, we can say. So this gives us 18 mg uh, by 18 mg. Tension would be simply 18 mg by 5, we can say. So here what we can say now, like this is the tension, and now at this point over here, uh, this would be experiencing a tension in this direction, and this would be experiencing a friction in this direction, and the critical value of this friction is going to be mu times n, and n would be nothing but mu mg cos theta. So mu mg, that would be 4 by 5 mg over here. Okay, so I hope like I have made this calculation correctly. So that is 3 by 5 mg, and mv square by L, and that was mg. We can take common 3 by 5 plus 3, so 5 3 huh. Okay, so the friction here we can find out simply will be equal to, like here it will be experiencing again mg effective, mg effective over here. So that would be 3 by 5 mg over here. So friction will be equal to T plus 3 by 5 mg, and that would be 18 uh, by 5 mg plus 3 by 5 mg. It will give us 21 by 5 mg, and that we will be equating it with this friction over here. So that would be 4 by 5 mu mg over here, and this will give us the value of mu to be equal to 21 by 4, we can say. So this was one question. So like definitely there can be many varieties of problems in circular motion in vertical plane, but since we are running out of time, we will be quickly moving on to another example, another topic over here. And that topic is the relationship between force and conservative force and potential energy. So let me open that file for you. So that is this one. Okay, so let's try to find out. 1 second. So this is potential energy. Okay, so potential energy and conservative force. So we have learned the definition of change in potential energy over here, which was simply du The work done, change in potential energy was negative of work done by conservative forces. Okay, and that could be written as minus F dot dr, where this force over here would be a conservative force in nature. Rearranging this equation, what we can write is F is equal to minus, you can say du, rather we must use some other symbols over here. What we can say, I don't know whether people are aware of this terminology or not. So that would be equal to delta, sorry, um, one second, del u. Okay, so that's simply an Cartesian coordinate system. What we can write is F will be equal to dou u by dou x I cap plus dou u by dou y j cap plus dou u by dou z k cap and negative of that. So if we know the expression for potential energy as a function of x, y, and z, and from that relationship we will be able to find out the expression for the conservative force in its vector form. Simply in two dimension, sorry, in one dimension, I must say, if the motion is along only x axis, the forces acting are only along x axis, so in one dimension, F simply could be written as F is equal to minus du by dx, and that is a very, very important relationship for us. F is equal to minus du by dx. This relationship let us establish the connection between the conservative force and potential energy. If we know the potential energy expression, we can very well find out the expression for force as well. So this enables us to study the um, condition for equilibrium of a particle in one dimension, we can say. So let's try to learn about equilibrium of a particle when we are looking at the energetics of the particle. So in order for the particle to be in equilibrium, F must be equal to 0. So if F is equal to 0, so that's definitely gives us du by dx. Since F is equal to minus du by dx, this has to be 0 as well. Now we will study the two types of equilibrium over here. One is stable equilibrium, I must say, and the another one is unstable equilibrium. As the name suggests here also, like stable equilibrium gives us the sense that it is stable. Like for example, let's take a illustrative example. Let's say this is some bowl over here and there is some particle over here. So what we can say, like this is and definitely a equilibrium position, and if we displace it slightly from its equilibrium position, let's say dx in this direction, we must understand that there would be a force which will try to bring it back to its stable equilibrium position, and if we displace it in this direction, this force would be directed in this direction. So like this type of force is known as a restoring force. And also you can notice like the direction of this df force is always opposite of the direction of displacement. Okay, so here the displacement was in this direction and force was in this direction, and here displacement is in this direction and force is in this direction over here. So from this we can definitely say the condition for stable equilibrium position, that df by dx, since the sign of df and dx are opposite, so df by dx is gonna be negative, and since f is equal to du by dx, minus du by dx, so what we can say that minus d2u by dx square is going to be negative, so that gives us d2u, double derivative of potential energy expression, is going to be positive. Okay, and similarly in unstable equilibrium position, let's take this example over here, and let's say there is a particle over here, and if we displace slightly, this is stable, this is an equilibrium position, an unstable one. So if we displace slightly, a force will tend to act which will further move it away from equilibrium position. Either it is in this direction, so df will be in this direction. So here clearly we can say that df by dx is a positive quantity. So d2u by dx square is going to be negative in this case. So these are the conditions for stable and unstable equilibrium position. Let's try to look at it graphically. Okay, so first of all we will try to learn it into f versus x graph. So f versus x graph, let's say we are having f versus x graph, and let's say the graph nature is this, for example. So first of all, we must try to find out where is the equilibrium position. So that is very simple. Wherever the force is zero, that is the position where there is equilibrium. So this is one position and this is another equilibrium position. These are the two values of x corresponding to which the force is equal to zero. So these two positions are stable. These positions are equilibrium position. And which of them is stable one and which one of is unstable? So here for that we need to look at the value of df by dx. If it turns out to be negative, that means it is stable equilibrium. If it turns out to be positive, it is unstable equilibrium. So at this point over here, when we draw the tangent over here, so we can definitely see that this angle is obtuse. So df by dx is definitely negative, and at this position this angle is acute. So you can say df by dx is positive one. So definitely this is a stable equilibrium position, and this here is unstable equilibrium position. And similarly we can do the same thing looking at u versus x graph. So if we have some u versus x graph like this, say like this, we have u versus x graph. Okay, so first of all we need to find out the equilibrium position. So for equilibrium we know that du by dx is going to be equal to 0, means the slope of this graph must be equal to 0. That means at the maxima or minima, either at this position, this value of x, or at this position, this value of x, we will be having equilibrium position. So which one is stable and which one is unstable? So for that, here we can see for the minima we know that d2u by dx square is positive. So that means this is a stable equilibrium position, and this over here we definitely know that d2u by dx square is negative. So this position over here is unstable one. So just by looking at the graph of either f versus x graph or u versus x graph, we can tell like which all positions are equilibrium position, and we can also identify that which one is stable and which one is unstable over there. So now very quickly let's cover one problem, and that will conclude our session. And this is the problem I am looking to solve over here. So let's use some other color pen. So this is the question: a block of mass 12 kg is located on a horizontal surface that is xy plane, and its initial position, let me draw some uh, picture also. So this here is xy plane, and let's say this here is origin, and this is x is equal to 10 is the initial position of particle, and the mass of the particle that is given to us is 12 kg. And coefficient of friction, there is on this surface is rough as well, so mu is given to us as 0.4. And this region also consists a conservative force field of potential. So expression for potential energy is given to us, that is minus x cube plus 75x minus 234. and that is for a mod x less than 6. So what we can say over here, like potential energy is um, uh, the conservative field is only in a region uh, for less than x is equal to 6, and it is absent in the region beyond x is equal to 6. So that is given to us, and what we have to do is find minimum kinetic energy with which the block must be projected. So block must be projected in this direction to reach the origin. So what should be the minimum kinetic energy for that to happen? So how we are going to approach this problem is, the expression for potential energy is given to us as u is equal to minus x cube plus 75x minus 234 over here. So what we can do, first of all, we can find out the conservative force, and that is going to be minus du by dx. Okay, and that will be equal to minus 3x square plus 75. Apart from that, when the particle would be moving in this region, let's say over here, it will be experiencing a frictional force as well. So this would be friction, and that would be nothing but mu mg, you can say, and mu is nothing but 0 0.4, and m is 12, and g is 10. So that is going to be 48 Newton would be the frictional force. So net force, when we will be calculating, is, that would be conservative force plus frictional force. So that would be giving us minus 3x square plus 75 uh, and sorry, I think I have made a mistake over here. The negative sign I have not written, so this will become plus and this will become minus over here. Okay, so plus and this minus over here and plus 48. So this is going to be 3x square minus 27 we will be getting. So this is the force. So here from this expression of force, we require to find out, uh, see, one thing I want to make it clear, like it has been asked to us that what should be the minimum kinetic energy, so that it must be projected from here to reach the origin. Okay, so here we need to understand first of all that it is not completely our job, okay, to push it till origin over here. Our job is to find out some position in between where where the force, net force, will be equal to 0, and we have found out this position as x is equal to 3. So at x is equal to 3, the force is acting in of x is equal to 3, the force is 0, and for x greater than 3, it is acting in rightward direction, means it is opposing the motion. But beyond x is equal to 3, that means less than x equal to 3, so what we can say, like the force would be in leftward direction, so it will be automatically pulling this particle towards origin. So our job is just to make sure that this particle, when it is projected from here, it reaches over here. And now we can find out, like initial position is x is equal to 10 and final position is x is equal to 3. So we can now simply use here work energy theorem in order to find out the minimum kinetic energy. So W external, or work done by friction, here will be equal to change in potential energy plus change in kinetic energy. So work done by friction over here from x is equal to 10 to x is equal to 3. So that will be simply minus mu, that would be 0 0.4 into m is 12 and g is 10, and x would be here equal to 10 minus 3, that is going to be 7 over here. So that is work done by friction, and change in potential energy is will be the we have to like the potential energy from here to here is equal to 0. So potential energy will be basically changing from here to here, x is equal to 6 to x is equal to 3 only. So a change in potential energy we will be writing at u is equal to u at x is equal to 3 minus u at x is equal to 6. So that would be the change in potential energy, since we know the expression for potential energy. But just by substituting 3 and 6 we will be able to get these values. And change in kinetic energy would be initial kinetic energy is k, and we will just make sure it reaches over here. So here it has to become 0, so that would be minus k, and solving this we will be able to get the value of kinetic energy as 300 joules. You can solve for that. So from with this problem I will conclude my session. And work power energy, I have tried to um, cover a few concepts as well as few questions. Uh, the next session would be about center of mass. Okay, so let me stop sharing. And okay, so I am on webcam now. So like do join me for the next session of center of mass, and thank you very